Well, I feel very comfortable in a session with a lot of geophysics because as much as it pains me to say this, I think we have something as geochemists to learn from geophysicists. So I've got that off my chest. I'm not going to hug any geophysicists, but I'm not going to get too carried away. But before I begin, I would like to acknowledge my colleagues that have helped with this project in various aspects, and I'd also like to thank Geoscience BC for supporting this work. So what I'm going to go through in the next 20 minutes, I'm going to state the problem and the reason why I selected the northern Vancouver Island area for this project. Give you a brief background to catchment analysis. I've spoken about it previously, so I don't want to belabor that point, but there are some key aspects that are worth covering. I'll present the results from the northern Vancouver Island study and then present some conclusions. So the reason that the Northern Vancouver Island project was important is from the previous regional geochemical survey data that was collected in the 80s, it was very difficult to see the porphyry copper deposits because the Karamutsan Formation basalts are elevated in copper. So we have this high regional copper background that disguises the signature that we might associate with the porphyry copper deposits. So really the challenge is how do we filter out that high background effect so that we can get back to using the data to actually see potential mineralization. So that was the challenge. So the way we've approached it, one is to look at a geology map in a slightly different aspect. So from a geochemical point of view, what's important is to look at lithology. So this is an unusual geology map of northern Vancouver Island where we've identified different lithological units that will have different background geochemical signatures. And here's the raw copper data on your right-hand side. The stippled area is the distribution of the Karamutsan Formation, and that's going to be retained on a lot of these diagrams I'm going to show. These maps, by the way, I'll show quite a few of these. These are gridded percentile images based on the point data, but at the end I'll show you the catchment maps that are included as part of the package. So really the problem is that we have the Karamutsan Formation controlling the distribution of copper mainly, but we also have something else which is possibly associated with the Mount Hall gabbros. Principal component analysis, I'm only going to mention this very briefly. For those of you that aren't familiar with principal components, one way to think about it, in this case I've got a 2D slice, if you like, through a cloud of data, in this case represented by copper and nickel, and we can define the axis as long as those two elements are correlated with the principal component and then an orthogonal direction associated with it. If we add another element, then that vector is going to be in 3D, and then we can go on into multidimensional space. And then from that principal component, we can drive loadings for the different elements that are included in the calculations. What I've done with those loadings is sort them, put them on a line chart, and you can see right away that we've got some negative loadings on principal component 1, which describes most of the variation in the data set that are clearly associated with mafic lithologies. So the key point here is that principal component 1 is lithologically controlled. So now if I plot principal component 1, or in fact the inverse of principal component 1 because they were negative loadings, but what I want to do is see the hot colors associated with our mafic lithologies. And you compare the inverse PC1 with the raw copper data. In fact, we have a better fit to the Karamutsan Formation when we use principal components, and that'll be a bit of a theme, that instead of relying on a single element, it's better to have multiple elements to help with the interpretation. So a few key points about drainage geochemistry. The things that are important are catchment size, which controls dilution, catchment geology, which gives us our variable background values and also can affect erosion. The relief in the catchment, for a lot of these calculations that I'll be presenting, we're assuming constant erosion throughout the catchment. We know that's not realistic, but it's the best we can do at this point. We may have scavenging of metals by various hydroxides, clays, or organics. affecting the geochemical data. Stream water EH and pH are going to be important for controlling middle solubility and also where hydroxides precipitate out into the stream sediments. Hopefully we've got some mineralization in the catchment, which is what we're looking for. And then we also have some issues with data. For example, the historical gold data in the RGS data sets is not particularly reproducible because of nuggety gold issues. So what I've done in terms of data processing approaches, of course, we've looked at the raw data already, and quite often that's where geochemists stop, unfortunately. But what we can do is if we do see an influence of a control element on an element of interest, then we can do a regression analysis against that control element. We can level data by dominant catchment lithology, or potentially even just the presence or absence of a particularly important type of lithology within the catchments. We can take all the lithological information from the catchments and we can derive a weighted background value. We can do a similar sort of thing by using a multiple regression approach, using the catchment geology. We can actually generate residuals for a particular element off a principal component. For example, if you can demonstrate a principal component is lithologically controlled and includes an element of interest to you, then you can do a regression against it and calculate the residuals. Productivity analysis, I'll describe this in more detail a bit later, but this brings in the effects of dilution. Weighted sums models, at this point now, we're bringing in multiple different elements into the modeling that we're doing. And then we can actually weight our weighted sums model with catchment area. So for this particular project, we integrated two data sets, the archived RGS samples that Wayne Jackman had reanalyzed, as well as in red, the new samples that he collected in 2012. And from that, on your right-hand side, we generated, I shouldn't say we, the British Columbia Geological Survey generated for us the catchments for those sample locations. But there are a few tricks to the trade, if you like, in terms of doing catchment analysis. One was validating sample locations, and one of the ways we went about doing that is we actually had scanned copies of the original topographic maps that were used by the sampling crews. And this is an example of some of the issues that you might have to deal with if you're doing this sort of work. Here is the mark on the map from 1988 where the sample was located. You can see in blue the modern trim drainage that we're using for the modeling purposes to generate our catchments. It clearly doesn't correspond to the drainage on the map. So we've had to take that point and we've moved it to that point so we capture both these tributaries. There's a problem with that tributary that we can't pick up. It's hard to say if that point just sampled this tributary and those two branches, or it came over here as well. So those are the issues that involve going through some sample locations point by point and making decisions about where to locate the samples. The other important issue in terms of looking at the catchments is quite often there are overlapping or nested catchments that we have data from. So for example, this catchment highlighted in red has an outlet down there. We really need to include that entire area when we're doing our calculations. So we have to have the geology for that entire catchment area for that particular sample and also that entire area for doing the calculations. So one of the things that became apparent in looking at the data was that there's a strong positive correlation between copper and aluminum in the samples. So one of the obvious things to do in that case, if it looks like copper may be controlled by the clay content in the samples, is a regression analysis against aluminum and then plot the copper residuals. And you can see now that we're starting to move some of the copper anomalies off the Carmoutzen Formation, and we're starting to pick up some of these other occurrences and deposits that perhaps weren't highlighted in the raw data set previously. The other approach is to level the data by the dominant catchment lithology, and this can be done to any elements really that show a correlation with particular rock type. So here's copper in this corner here, and you can see in red basalts have high copper, and when we level the data, it brings everything back into sort of a central tendency, and then really what we're interested in are the statistical outliers in the data set, because those are our geochemical anomalies. So this can be done two different ways. On your left, the data have been leveled by the dominant lithology. On the right, the data have been leveled simply using the presence or the absence of basalt in the catchment. And you can see both of these products are very similar. And obviously just doing a binary sort of leveling presence or absence can be a very simple thing. To get a little more complicated, though, if we want to bring all the lithological information from the catchment into the calculation, what you can do is a weighted background value, whereby if we have three different geological units in a catchment, each having different background concentrations of, for example, copper, and we know the proportions of those bedrock units within the catchment, then we simply weight their contribution to a weighted average for the catchment. That becomes our background value, and then we can look at the difference between the background value and the observed value for that particular catchment and plot the residuals, and we end up with a product like that, which doesn't look dissimilar to the previous products that we looked at. So if I flick back, you can see that we're getting subtle differences between the two different products, but they're derived in a very different way. But the consistency in terms of some of the anomalies that are coming out using these different processing methods is encouraging that some of the anomalies are actually real. I mentioned this previously. One of the things you can do if you can demonstrate that a principal component is lithologically controlled, such as principal component 1, we can do a regression against that principal component using copper, and then look at the residuals, plot the residuals, and again, we've tended to move the copper anomalies off the Carmoutzen. We still have that Mount Hall-Gabbro anomaly, because that's not, if you recall from an earlier slide, wasn't accounted for in the Carmoutzen signature from principal component 1, and really these high residuals represent areas of elevated copper that we're going to be interested in. The next step is to start to incorporate more elements into the whole process. So that can be done using a weighted sums model, which requires some a priori decisions to be made as to what commodity or pathfinder elements are going to be important for the target deposit that you're looking for. And so the thing about using a weighted sums model rather than a simple additive index is that you can weight different elements depending on how important you think they should be contributing to the geochemical signature from that deposit. And you can even use negative rankings to take elements out that you want to discount for that particular model. So, for example, for a porphyry copper model that I generated for this project, I used copper, moly, silver, raw gold, leveled data for everything else, but raw gold data and leveled zinc using these rankings. And one of the things that it's done is up in this area, some of the occurrences and deposits that weren't coming up just using copper are now visible when we use a basket of different elements. And again, we've moved everything pretty much off the Carmoutzen. So the next thing to deal with is the effects of dilution in terms of how that's going to affect the geochemical signature that we're seeing in the stream sediment data. And this is a very common plot for anyone that does a lot of this sort of work. We can plot really any geochemical indicator on the y-axis plotted against catchment area, and typically you see this decay away to regional background values. So as people familiar with stream sediment data are probably aware of, the best anomalies tend to occur in small catchments. So at about an area of 10 square kilometers, we've really dropped away so that we're getting down to background values. So most of what we're seeing in these larger catchments is going to be regional background. But those become opportunities for follow-up sampling. And so what we've done is we've done a map of sampling effectiveness, which indicates in orange those catchments that are greater than 10 square kilometers and could benefit from follow-up sampling. The other approach to incorporating that now with the geochemistry is something called productivity analysis. I won't go through all of that, but the key bit is the simplified formula, which is the metal content at the mouth of the catchment minus the background value, and then multiplied by the area of the catchment. And so the copper productivity map using the background weighted value is shown here, and you can see that we're picking up some of these occurrences and deposits still much better than if we used a copper-only type model. So the question becomes how to assess or how to validate these different data processing methods. People involved in mineral exploration will be familiar with this terminology. We have catchments where we know we have copper occurrences, and we have catchments where there are no known deposits or copper occurrences. I've used a 90th percentile cutoff for all the different methods that I've used for data processing. So what we want to see are true positives. We don't want to see false negatives. We certainly know where the current copper occurrences are, so I can use that as a way to test the different methods that I've utilized. So if we start with raw copper, which had about 13 catchments with true positives, but I'll put that at 0, and then I'll look at the percentage difference as we start to apply these different processing techniques. So these are all a basket of single element methods that I spoke about at the beginning. And you can see right away we get a significant increase in the number of true positives, which indicates straight away the benefits of doing some sort of data processing to the raw data. And they increase up to as much as 120%. If we bring in the effects of dilution or we bring in other elements, we get another bit of a kick. And then if we combine the two, a multiple element model or weighted sums model with catchment area, that gives us the best response in terms of increasing the number of true positives. At the same time, we also decrease slightly the number of false negatives. So, to conclude, the effects of the high copper background are relatively easily dealt with using different methods of varying sophistication depending on what your biases and favorites are. But what appeared to work best is a method using multiple commodity and pathfinder elements and also integrating the catchment area into the process. And this has resulted in a better recognition of existing copper occurrences and deposits, as well as generating a number of new anomalies that are not associated with known copper mineralization. And because I'm seeing these in multiple products, I have confidence that they are probably meaningful anomalies. They may not be related to mineralization, of course. There may be something in the geology that hasn't been recognized that may be the explanation, but certainly they're areas worthy of follow-up work. Plus, an empirical assessment of sampling effectiveness indicates that there are still opportunities in quite a large portion of the study area that are undersampled, I would argue. And in fact, I would say as a general statement or conclusion that there are a lot of opportunities going back into the existing RGS data sets. A lot of those catchments will be quite large. They've been effectively undersampled. I speak to a lot of exploration geologists, and if they don't see anything in the existing RGS data, they tend to write an area off. But really, you need to look at the catchments represented by that data, and in fact, on average, I would say that up to 40% of the areas have been undersampled and are still open for further exploration. And then finally, I'll have to try to live down this statement with my geochemical colleagues, but I think we need to learn something from geophysicists in the way that they process data and they apply filters to the data, and they get much more out of their data interpretation by doing that. And I think as geochemists, we can do that as well. So I'll leave it with that. And just finish off to say this report was completed earlier this year, is available off the Geoscience BC website, and just show you an example of one of the final products where we've now done a thematic map using the catchments, and we provide a shapefile of the catchments with the attributed data associated with it, so you can generate your own thematic maps, use your own color schemes. I know these are the things we agonize over as geochemists. So thank you very much.